Hello friends and welcome back. In this video we'll be talking about Newton's universal law of gravitation, one of the most extraordinary and fundamental results in all of science ever, and like a gorgeous unification of loads of observations that astronomers had performed over centuries, and allowed Newton to put all of that and more, and the behavior of falling objects close to the surface of the Earth in a coherent and rational structure. Just a monumental result and wonderful science. I'm sure you know this already, or you've seen it somewhere. If you have two masses, m1 and m2, where at a certain distance r, right, this is a distance r, or this is the vector r, if you want to look with vectors, then the gravitational force between the two, force of gravity, this Newton says, is big G, the product of the two masses, and divided by the distance squared along the direction of r with a minus sign. Now let's talk about the various components of this expression, because this might look intimidating. There's a lot of new stuff maybe, but let's look at these things one by one. Now, first off, magnitude. What is the magnitude of this force? Is we take the absolute value, so Fg is simply this big G that I'll talk about in a second, the product of the two masses divided by distance squared. So it's the usual inverse square law, same as Coulomb force for electrostatic interactions, for example. I'm talking about this exponent in the denominator. And where this G is called Newton's constant, and it's in SI units, it's equal or roughly equal to 6.67, and I think there's maybe a 4 and a 3 times 10 to minus 11, the appropriate units. What are the units? Well, we can see it from the expression for force. It's newtons times meters squared divided by kilograms squared. And I believe that actually do it. If you work this out, especially in particular what Newton means, you'll find that this is meters cubed, kilograms minus 1, and seconds minus 2. All right. Fact check me, but I believe this is correct. All right. What else? Secondly, R. Actually, let me shrink this page just a second. There we go. Second aspect is r hat. This is the unit vector in the r direction. This will be r hat. And so this implies that it's directed, that the force is directed along the line joining the two masses. Okay, great. So it's a radial force in that sense. It's always directed along this line. And last but not least, importantly, this minus sign, the minus sign implies that the force is attractive. This is the general feature of gravity that, for example, does not apply to the electrostatic interactions. You can have attractive or repulsive electrostatic interactions. For gravity, it's only attractive. As it turns out, Einstein sort of explained why that is, but even at this stage, this minus sign is what explains that, and the fact that the masses are always positive. There's no such thing as negative mass in physics. From this expression for the force that I will actually just write again here, This is G m1 m2 divided by r squared r hat, or for a vector or just magnitude is G m1 m2 divided by r squared. So this is the force. We know from Newton's second law that force and acceleration are extremely connected. Oh, what did I write? Acceleration. Oh my word. Are have a great relationship. Have a very strong relationship. And so, what is the acceleration of gravity? Typically, we write it as g, and it's simply the force of gravity divided by the mass that I'm considering. So let's take, for example, now let's change nomenclature and do m, little m and big M. So I'll go here. So what is then the acceleration of little m? It's the force of gravity that's experienced by little m divided by the mass itself. So I would take this force and I will divide it by the value of the mass itself. What is the magnitude of this acceleration of gravity? Well, it's the same, Fg divided by m. And so in this case, it will be equal to, let me make some space. It's equal to g Newton m big M divided by mr squared. So I just cancel m out and I rewrite it as big M divided by r squared. Look at that. So as a result of the gravitational interaction of two objects, little m and big M, little m in this case is experiencing an acceleration that is equal to this value. Now, this is especially important when we talk about one of the approximations for the law of gravity that we already talked about in Intro to Physics, which is F equals mg, near the surface of the Earth. Take, for example, a person or an object close to the surface of the Earth at a certain altitude h. There's an object here of mass m, and this is the Earth. The Earth has a huge mass. This is roughly 6 times 10 to the 24 kilograms, and had a pretty sizable radius. The radius of the Earth is roughly 6,371 kilometers. Okay. Now, what does this expression translate to in this situation? Well, so the acceleration of gravity is big G, the mass of the Earth, divided by the total distance between Earth and this object that I'm considering, which is the radius of the Earth plus whatever altitude this object has squared. And now look at this. Given that these two quantities, namely the radius of the Earth and altitude, are very different, one, and you can probably tell already, say which, greatly dominates over the other. So in situations where the altitude is completely negligible compared to the radius of the Earth, and notice that with the radius of the Earth being several thousand kilometers, there are even significant altitudes like hundreds of meters or even tens of kilometers are completely negligible compared to that. So this is roughly equal to g, mass of the Earth, divided by the radius of the Earth squared. Okay? Plus small correction that depend on this little h. And lo and behold, this combination is not a coincidence that that I call this acceleration g, because this is precisely the g that appearing in the approximate expression F equals mg. All right, this is exactly that. By the way, Cavendish, who is credited with measuring for the first time the value of Newton's constant g, which is not easy at all. Actually, in his paper or his work where he presented this result, he actually phrased it as I measured the mass of the Earth, because it's not as simple as you can imagine, as you may imagine, to measure the mass of the Earth. The radius of the Earth is pretty simple. The Greeks knew it. The acceleration of gravity g is fairly simple. You did it yourself in PHY1001 or PHY1002 with the pendulum. But the combination g times mass of the Earth, this is tricky to, either of these two things is quite tricky to determine. The combination is not. And so Cavendish phrased it as I just measured the mass of the Earth. Really, really interesting. All right. You may be interested to know, on top of this, that the gravitational field is actually the same thing as the gravitational acceleration. Okay, so when you say, see, the gravitational force depends on, so in particular, this is equal to the force experienced by a certain mass divided by the mass itself. And this is kind of universal. It doesn't depend on the mass of the objects, on the shape of the object, and all of that. So that's why it's called field. It's a property of space. No matter what, if you have a distribution of masses, and then in this distribution you place a little object of mass m, the gravitational force experienced by this mass will be the combination of all the forces that this mass is experiencing as a result of these surrounding objects. But the gravitational acceleration or field is universal. So if you take that force, the net gravitational force, and you divide it by m, this is the gravitational field, and this is universal, which is absolutely, it's wonderful. And if you go forward in your studies with Einstein, you will also, and study general relativity, you'll get to know even more about this universality, but it's, yeah, even at this stage, it's a very beautiful result. This is maybe a good moment to talk about systems of particles or extended objects. We won't do a lot in this context in this course, but it's good to know, because, well, the world is not just made of point particles. In many situations, you have either a combination of objects, like I actually just mentioned in the previous on the previous blackboard, where there's a thing called superposition principle. Superposition that says that the total force as a result of gravity experienced by m is the vector sum, denoted by this symbol. This is the sum over all the masses surrounding it of g times the mass that I'm talking about, the I mass, the distance to the mass I, and what I mean by that is if we label these m1, m2, m3, m4, each at their specific distance, this would be r2, this would be r1, and so on and so forth. And I need a minus sign and the unit vector in that direction. This vector sum is the net gravitational force acting on the mass. It's crucial for you to remember that this is a vector relationship. It's a vector sum. So I'm not just adding the magnitudes. And that's very important. And this connects, actually, maybe explains even better what I just said about the gravitational field, because the resulting gravitational field is simply this force divided by the mass m, and this is simply the sum of minus g mi divided by ri squared in this direction. And as you can see, there's no appearance of the mass m in this expression. So any object that I put inside this configuration of masses, it will experience the same acceleration, which is really, it's really a fantastic result. Those of you that are passionate about calculus and derivatives and integrals in this case may be interested to extend this to a composite object where instead of systems of particles, I'm taking into consideration the effect of every little element dm of this extended object. Okay, and the result is that the gravitational force experienced by my mass under consideration is some integral of the forces that each little dm exerts on this object, which is minus g, the mass of the object, and this integral of dm divided by the distance squared times r hat. In practice, we won't do this all that much, because just, I don't know, taking nasty integrals is not is nobody's favorite thing, at least not mine. But at least conceptually, it's good to know that the superposition principles implies that just taking an integral, it's no more complicated than taking an integral to calculate the overall effect of any extended object when it comes to gravity. Last little detail that you may be interested in knowing is that most of the times this dm, you'll find it written as rho times d volume. So rho is mass density that in many problems might be constant, because it's simpler to discuss a uniform an object with uniform density, but it doesn't have to be, and as in principle depends on the position. And dv is the infinitesimal volume element. So when we consider one of these dm's, this is, you imagine it's a little cube of volume dv with a certain density rho, so the little mass is mass density times volume. All right. We conclude this video by mentioning the all-important and extremely beautiful shell theorem by Newton that we won't prove explicitly, but any good textbook has a demonstration of the shell theorem that you can go and check out if you're interested. But the two main results of this theorem are that, one, a spherically symmetric distribution of matter has as a gravitational effect to an object outside it, it's the same as a point particle of mass equal to the total mass of this spherically symmetric spherically symmetric distribution located at the center. So as far as an external mass is concerned, this extended, maybe humongous, but spherically symmetric object is the same as having simply a point particle here at its center attracting it. Maybe let me draw it better. There you go. It's the same. Okay, this is result number 1. And result number 2, maybe slightly less intuitively, because I don't think this is especially confusing, but this might be, is that a spherical shell of matter, okay, actually doesn't matter if it's like a thin shell or not, but a Newton, it's easiest to demonstrate for a thin shell, and then you can extend it to a finite shell. A spherically symmetric shell of matter, of uniform matter, has is such, like acts in such a way gravitationally that no gravity is experienced by objects inside. Maybe let me rewrite this a little more nicely. Inside it. So wherever you put an object in here, even though, and I agree with you, this portion of the shell is definitely closer to the mass, and so in principle these points would pull more strongly, whereas the points that I'll draw in red, maybe on this side, definitely pull less strongly towards my mass. Because of the larger distance, there's more of those, and somehow the gravitational interaction, gravity from all points on this shell is such that this mass, anywhere you put an object inside, there's no gravity, no gravitational force, which is really incredible, and which we'll use because it simplifies calculations in a great manner whenever you have a spherically symmetric object. The typical case that we consider is the following, where you have an extended object that's spherically symmetric. Doesn't mean that it's uniform, by the way, but simply spherically symmetric, meaning that whatever happens, so for example, it may have, let me draw it again, it may have a core, and then a hollow section, and then a small uniform shell, and then another hollow section, and then a more extended region that's full. Well, if you are at any location inside this object, what matters to determine what the gravity is at this point P is only the inside of a sphere that starts at the center of this distribution and ends at P. So the yellow part, yes, contributes. Anything outside of it, well, for that you can apply the second lemma to the shell theorem, which is that a spherically symmetric shell doesn't affect the insides. And so, pardon my awful drawing, but I hope I made, in my words, explain it. When you talk about a spherically symmetric distribution of matter and you're inside it, the only gravity that matters, that affects your behavior and your motion and your properties, is the gravity of what's sort of below you towards the center and not above you, which is a very mysterious and maybe counterintuitive and very beautiful result. All right, friends, thank you for so much for watching, and I'll see you soon.